Thank you very much. My name is Hamza Shakeel and I am a postdoc at National Institute of Standards and Technology. So this work was done in collaboration with Tom Metcalf from NRL and today I'm going to talk basically the thickness dependent of quality factors for a double paddle oscillator at room temperature. So this is how my presentation is structured. So I'll start with the motivation, then I'll move towards explaining some of the salient features of this particular oscillator called DPO in short. Then I'll explain the fabrication process involved, and then I'll move towards the results section where I have short experimental and analytical results. Then I'll show you some Fem simulations, and in the end I'll summarize my talk. So starting with the motivation, so these sensors or oscillators are basically used as a mass sensor in our application. So ideally, everyone wants to operate these oscillators or any oscillator at ambient temperature or pressure conditions. So in our application, so one of the main motivation was that handling of these particular oscillators. I'm going to show you in the next subsequent slides as well. The reason for saying that part of the issue we had was since the dimensions of these oscillators are in millimeters, it's not like, for example, we're going opposite route of what everyone has talked. So in our case, dimensions are in millimeters. So when we have very thin wafers or thin devices, so handling of these becomes very critical actually. So we wanted to analyze if we move towards thicker devices, will that help us in terms of increasing the mass sensitivity? Because for increasing the mass sensitivity, we have to, everyone is talking about that we have to decrease its size of the device. So in this talk, I'm going to talk about three different thicknesses that we have used, and then I'll compare the results at the end. So what is the main motivation for using these particular type of oscillators? So in going with the scope of what NIST does, basically we are using these to quantify how mass varies over time. So if some of you have heard that there is a very big actually international effort to redefine mass or to redefine kilogram in scientific units. But even if it's redefined in next couple of years, so we'll still face this problem that the artifacts that are being used to either calibrate or compare masses, they still drift over time. So there is, it's reported that the mass artifacts, they almost drift like by 20 micrograms in 5 years. So we want to quantify those mass drifts, and we want to basically have some kind of a model actually. And apart from that, these type of oscillators have been used in different applications. For example, to measure how the in this case, in this for example, what we did was that we measured some of the thermodynamic properties of different atmospheric gases at very low temperatures. Some of the groups have used these to measure the elastic modulus of graphene films and measure internal friction of different films. And probably at the end of this talk, you will realize what is the reason for using these type of oscillators for these type of application. And another motivation for me to present this work at sensors was that I come from a sensors background or MEMS background. And most of the work that I saw on double paddle oscillators, it was more, I think, physics related or more fundamental science related work that is being published. So I just wanted, for example, this community to know there is another type of oscillator probably that might be helpful for any other type of research. So this is how our setup looks like. So this is the main assembly. This is the oscillator that we install. It has different parts that is shown in this diagram: wings, leg, neck, and head. And it is fabricated using very standard processes that I'm going to explain in the subsequent slide. And it is installed in a very high vacuum chamber and then actuated electrostatically. There are 2 electrodes underneath each of this wing. And this is special, or the mode that we operate this sensor at it's called anti-symmetric 2 mode. I'm going to show animation of that mode. And with this mode, the sensor is, the resonance frequency is around 7.5 kilohertz, and quality factors are in the range of 400,000 for 400 micrometer thick DPO, and it improves further if we go to cryogenic temperatures. Now, this leads to, with high quality factors, we have a very high mass sensitivity, which is good for our application, which we want to basically detect around 20 micrograms drift over close to, I think, a year. Now, the fabrication of these DPOs start with the clean RCA clean silicon wafer. We deposit LPCVD silicon nitride on both sides, and then do front side photoresist process. Then we cleave the wafer into two halves that will expose the 110 plane. So this is a crucial step in fabrication. Part of the reason we want to align our pattern, which is shown on this diagram, is that we want to have an isotropically etched device. And for that, we have to align our pattern with this exposed 110 plane. So we do contact lithography, and then afterwards dry etch nitride. Then this will give us a hard nitride etch mask that we are going to use for wet etching. So this, after wet etching, we get the features are trapezoid, and this is around angle of, I think, 54.7, I guess. I think it's close to 55 degrees. Now afterwards, we remove the nitride and then deposit gold electrodes on the reverse side of the device, and then these are used for actuation and detection. Probably I should have put the slide in the front. So this gives you an idea about the dimension of the device on the left side. So A is around 20 millimeters and B is 28 millimeters. So it's pretty big device in terms of if you compare it with other work. And we could actually shrink this device, but the reason that we didn't do that is that the artifact, the surface area of the artifact, kilogram artifact, is close to I think 6.5 centimeters square. So that was the main motivation of designing using these dimensions. So on the left side, we have fabricated devices. Even though we have a rectangular feature for all of these wings, head, and foot, what we get after etching is some of these convex corners get under etched. So this is we are trying to avoid this in our next design. Now, the experimental results were performed. We did regular frequency sweep to identify different resonance modes, and then self-excite in this anti-symmetric 2 mode, which gave us pretty high quality factors, and we used very standard lock-in measurements to get the ring down measurements, and we used a self-tracking mode actually, and which becomes more critical if we are depositing different films on top of it during different measurements. Now, with this experimental results, we got kind of a trend that with each increasing thickness, our experimental resonance frequency for this AS2 mode was increasing, and similarly, our quality factors they were also increasing. So we knew that if we go to thicker dimensions, so it's going to be helpful for us, because it's going to, during handling, during fabrication, and during installation of these oscillators, it will be a lot easier. So we wanted to go actually further than 500, but for that we had to change our design. Now, analytical model, I think our invited speaker, he was talking about thermoelastic damping, and it's a pretty, I think, a classical expression for that. So there is only a slight modification that is done for this particular oscillator. So there is a modal participation factor for this particular mode. So looking at this expression, there are like two terms. One is thickness independent term and thickness dependent term. And in thickness dependent term, we have thermal relaxation time and frequency. So both of these are again dependent on the thickness of our oscillator. And if we see, if we just plug in the values for the constant for different coefficients in this equation, so what we see is that empirically that if we increase the thickness of our DPO, so this term basically reduces. So the effect of this term reduces. So that basically corresponds to the increase in the quality factor. So there is another analytical expression for the frequency of AS2 mode, and that also has again thickness dependence. And some of these terms here, for example, C, D, E, and F, these are related to the dimension of the head. So once we move to the next stage where we are planning to optimize its geometry, so what we see from this particular expression is that uh, CD, for example, is the dimension of head. So we have room to shrink the head of our oscillator. So that is going to help us increasing the quality factors further. And overall, we get the same kind of trend that both frequency and the quality factors are increasing according to these expression. So we then used FEM simulations, and motivation for doing FEM simulation after we already know what the trend was, that we were planning to change the geometry and also increase the thickness of our device further to move to let's say a millimeter thick DPO. So we wanted to see how that will affect. So we used COMSOL for that, and one thing we included in our simulation is that we tried to incorporate material anisotropy, and then we also tried to incorporate the, uh, basically how the plane of this or the axis of this was aligned to a proper crystal plane in the model as well. And the COMSOL simulation basically showed we only simulated 10 resonance modes, and this is a very, I think, classical cantilever motion, which for our experiment showed low quality factors. Then this is simple torsional mode, where you can see that uh, the sensor is basically rotating at its axis. Then there were a couple of other low Q modes, for example, windshield wiper. It moves like a windshield. And then there is a flapping mode, which actually looks pretty cool. And then the two modes that I was talking about, there are two actually anti-symmetric modes. One is 1 and the second one is 2. So it's a little bit hard to basically see what is the difference, but if you just concentrate on its head and wing, you will see that both of these are in sync. And in 2 mode, it's out of sync or out of phase. So although we see FEM simulations show that AS1 has high quality factors, slightly different quality factor, but experimentally, AS2 mode has a better quality factor, and it is a lot easier to excite this mode as well. Since it was thermoelastic damping, so we also wanted to see plot the temperature deviation and see where basically temperature is changing at which of these. We want to identify the spots as well. So this just shows actually the points where temperature is increasing and decreasing, and how power is dissipating because of this temperature gradient. Now, with this, we again saw the similar trend, so that was expected as well, that both of these are increasing with the increasing thickness, both quality factor and the resonance frequency. And one thing that we wanted to, actually I'm already working on improving that, is how we can basically reduce the deviation between simulated and experimental values. And as I was showing you earlier in initial slides, is that there was some corner undercutting, and that was not incorporated into our model. And because of that, I think there is a deviation. And if you see that, for example, in these two tables, for a thinner DPO, the deviation for this AS2 mode is smaller. And as you go to higher dimensions, higher thickness, for example, 500, this becomes higher, even higher than this actually. And part of the reason is that there is more undercutting when you go to thicker dimensions. So this could be easily actually compensated. It's not a very difficult problem. And in the end, this just shows you the same trend for all the results. And I'll move to the summary slide so that we have time for some questions as well. And this just shows that we compare different methods to see how our thickness will improve the quality factors. It includes the analytical modeling, experimental results, and simulations. And in the end, I thank audience who actually waited patiently for this presentation. And thank you very much.